So now part three, let's talk about what happens around a big excavation underground, which is of course of great importance to mine stability and the safety and of mine workers, and also uh, the fact that you've got lots of mining equipment, quite expensive stuff down there. So if we consider this West Australian state of stress that I mentioned before, reverse faulting state of stress, so fluid pressure, vertical stress in the black line, um, intermediate horizontal stress in green, and the most compressive horizontal stress in red, with the numbers shown there. Pore pressure 15, vertical stress 39 MPa, least compressive horizontal stress maybe 56, most compressive horizontal stress 86, something like that. And that's at 1,500 meters of depth. So that's a common depth for many mines, the deeper mines in West Australia and Australia in general. In the situation in other places in the world is quite different, so they get as deep as say 4,000 or 5,000 meters in South Africa, but it's probably a different state of stress. So let's consider now what we're going to do with the mining. So I've shown in the left diagram a tabular slope, meaning a tabular stope rather, at 1,500 meters depth. So if we're talking about the Yilgarn, maybe the ore deposit strikes north-south, and remember from the previous diagram that I showed about the in situ stresses, we're talking east-west compression. So S subscript capital H is the big arrow, horizontal stress compressive, perpendicular to the stope, and S little h is the intermediate principal stress, or the horizontal north-south stress, the intermediate between the vertical stress and the maximum stress. And then the vertical stress is the least compressive of the three stresses. So that kind of situation, that stope is what I'm going to consider. It's possible to think about what the stresses would be around things like declines or ore drives and things like that. But the fact is, the stopes are the biggest excavations that cause the most impressive changes in the state of stress. So I'm going to talk dominantly about what happens with stopes as opposed to drives or declines. Okay, so if we consider the state of stress that I mentioned before, the pre-mining state of stress, that would plot on a Moore diagram something like the light blue line. And what I've done there is I've considered the pore pressure. So remember that with an elevated pore pressure or a non-zero pore pressure, the normal stresses are reduced by the magnitude of the pore pressure. So I've taken the stresses 86, 56, and 39 and reduced them both by the value of the pore pressure, or 15 MPa. So that's a pre-mining state of stress before we're dewatering, and assuming that we're talking about a hydrostatic state of stress where the water pressure is just related to the height of the column, and that would be either fresh water or brine. Uh, might make a big difference how salty the water is. So then if you consider, well, what happens to the state of stress as you pump out the water and mine down to the depth we're talking, 1,500 meters? Well, you're going to dewater the area, so that means your pore pressure is going to drop down to zero. And if you recall, what happens with the Moore circle diagram is that means the effective stress, which is typically plotted on the Moore diagram, will move further away from failure, or it will move to the right. Higher effective stresses because you're not reducing them by the pore pressure. So then you arrive at the 3D Moore circle shown by the light purple or dark purple lines. So that's the pre-mining. And now we're going to consider, well, what happens if we take out that stoped area? So remember, the stope is perpendicular to the most compressive horizontal stress, or S capital H or SH max in the other terminology. So right at the wall of that stope, because there's no shear stress involved in the stope wall, no stress on that wall, SH max got to drop to zero right at that point, right at the wall. So what I've done in the bottom diagram, you can see the dashed red line is if we move that stress right over to zero, the state of stress is going to look something like the black Moore circle, 3D Moore circles. And that's a very crude approximation. And the reason it's a little bit crude is because the implications or the reasons that it's a little bit crude is because we're relaxing the stress normal to the stope, the other stresses may relax due to what we know as a Poisson effect. That means that if we unload perpendicular to the stope or normal to the stope, there's going to be some potential reductions in the other stresses. So what was the intermediate principal stress, um, horizontal stress that's parallel to the stope, the S little h or SH min, that is probably going to reduce for sure. And then we may have some reduction in the vertical stress, but it's likely that that actually might not reduce very much. But in any case, then what we might do is evolve from the black state of stress in the Moore diagram to the purple one, where we reduce that the most compressive stress just a little bit. Might mention here that the failure envelope in red, it's a shear failure envelope, considers the conditions for Moore Coulomb failure with a UCS or an unconfined compressive strength of about 100 MPa. If the rock is weaker, we might expect failure of the intact rock to occur because of this change in stress. So if there's particularly weak types of rock, like maybe the ore is much weaker, or if there are very altered or weathered zones, we might expect some failure. The other implication is if you have a failure criterion for frictional surfaces, which might be typically shown in gray, that would be a friction sliding coefficient of about 0.6. Then a wide variety of orientations of faults or fractures, if they're present, will be at failure. So we can expect slip or reactivation on favorably oriented structures. And perhaps the most important thing is we have now swapped from a reverse faulting state of stress to a strike slip faulting state of stress, because the vertical stress is now the intermediate principal stress. It's quite close to the most compressive horizontal stress, which is now parallel to the stope, or if we're talking about Yilgarn, where the ore deposits are typically north-south, the north-south state of stress has now become the most compressive one, and it's a big change from the east-west state of stress being the biggest one. And that is a change that's essentially entirely due to the unloading of creating the unloading effect of creating a large open void or stope underground. So for this geometry, we know that SH max, the pre-mining SH max, will drop to 0 at the stope wall. So this local change in stress is extreme by any stretch of the imagination. Typically in the oil and gas industry, we talk about, well, the biggest change in stress has to do with depressurization or taking the pressure out of the reservoir. But this is a big deal. So at depth, we're causing a big change in stress. We're also going from a reverse faulting state of stress, shown in plan view as the blue region, to a strike slips faulting state of stress that'll be somewhere, and there'll be a transition between the two, somewhere between the far field, far away from the stope, and getting close to the stope. So the stope is the light gray area in the middle, shown as S. So the details of the orientations and magnitudes are complex and not necessarily easy to understand. Some kind of modeling is probably the best way to illustrate and understand the evolution. So boundary element methods, finite element methods, discrete element methods can all be used to give you a better picture of what the stress orientations are and how big the area where the state of stress is changed in this extreme manner is. And then also you can also then figure out, well, if you had structures pre-existing faults in different orientations, would they be likely to be reactivated? And that, in a sense, is a powerful predictive situation to be in if you can get there. So just a little aside on the magnitude fault area relationship, or the relationship between the two. So think of it this way. In general, the energy released in a seismic event or an earthquake correlates with the area of the fault that actually slipped. And that's an approximate relationship. It does depend on a number of factors. But in general, there's a well-known relationship between fault magnitude and fault area. So with mine seismicity in the Yilgarn, we're probably talking events of magnitude 1, 2, or 3. They're at the top of the table. The fault area in square meters is then shown for magnitude 1, 2, and 3 is about 900, 10,000, or 90,000 square meters. So let's focus on the magnitude 2. That would require an area of about a hectare or 10,000 square meters, or an area of 100 by 100 meters. So think of it this way: if you're going to make a magnitude 2, you need a pretty big area. It might be smaller than 100 by 100 meters, but it's probably going to be bigger than, say, 10 by 10. So it's bigger than the kind of excavation size that's typical anyway. It's certainly bigger than a 5 by 5 meter decline, or an ore drive that's also typically something like 5 by 5 meters. So the only other thing to say here is, well, we hope that we're only going to experience magnitude 1 and 2 in our lifetimes. I think magnitude 3 is rare, and I'll talk a little bit about how why I say that. Okay, so back to the earthquake size. So if we wanted to say something about, can we constrain the size of the earthquake that we might expect, one thing we could do is try to find the biggest fault that we think might slip. Well, if we're changing from a reverse faulting state of stress far away from our mining to a strike-slip faulting state of stress close into the stoping and the excavations, then we might think that, and it would be reasonable to make the assumption that the size of the fault that could slip would be related to the size of the area where the stresses have changed. So if we look at, say, a stope that's 100 meters long, 50 meters long, something like that, and similar dimensions vertically, and oriented approximately like I mentioned before, we might expect the area where the stresses are strongly changed to be sort of on the order of 100 to 300 meters. And of course, as I mentioned, modeling and some detailed calculations about how the state of stress would evolve as you move out after the stoping and away from the stoping, that would be a great way to try to figure out, well, how big is the area where the stresses would be close to failure and you might expect seismic slip. But just sort of crude estimate, if we have a stope that's typical of mining sizes in West Australia, I think it'd be fair to say that the area where the stresses will change is on the order of 100 to 300 meters, and that would be a substantial change in the state of stress. And we might expect to find a fault that would be on that same order that might slip in a single seismic event. So that's how I come up with the estimate of about 2 to 3 is the largest magnitude we might expect. But as I mentioned, this should be done in careful detail involving modeling studies to decide how big the area is where we might expect failure.